Hi guys, we're back for more, aren't we excited? Here's Unit 6, Lesson 5, Linear Models. So just a quick review about the line of best fit. It stretches across the data. It's this orange line right here. And although the data will often follow a specific trend, they do not form a perfectly straight line. If I connected all of these dots, my line would zig and zag all over the place. This line of best fit is just kind of like an imaginary line that goes through the points the best it can, okay? This lack of uniformity makes drawing conclusions about specific data points within the set difficult. So the problem with the line of best fit is that each person's line of best fit might be a little bit different. Like mine, I probably would have put a little bit more down here so that it ran like through this point instead of above it. There's no hard and fast rule for a line of best fit. So we're going to talk about least squares regression in this lesson. It's more accurate than the line of best fit. There's only one correct answer for a least squares regression. It doesn't matter who does it, everyone's line is going to be the same. It determines the best fit for a set of data by squaring the distance each point is from the line of best fit. It calculates an exact line, the least squares regression line. So this is how you calculate the least squares regression line. You measure each residual, the distance from each point to the least squares regression line, and square it. So the distance from this point to the least squares regression line is called the residual, and we're going to square that. And the reason that we square that is some points are above the line and are positive, and some are below the line and are negative. So if we left these as positives and negatives, they would cancel each other out when we add them together. When we square them, then we can find the actual true error. Like this is an error and this is an error, and we need to add those together, not be like, well, this fixed this a little bit. No, it didn't. It's this much wrong and this is this much wrong. This didn't like somehow make this more correct. Okay, so that's why we square it. Okay, now don't panic. We don't have to do this. We're going to use technology to do it. Models a linear function and can be written in slope-intercept form y equals mx plus b. Okay, this is impossible to calculate by hand. Yay! So we get to use technology, Algebra.com. It gets to do all the heavy lifting for us. Yay! Here's a check-in. What is the difference between the line of best fit and the least squares regression line? Look at this. While people often use the terms line of best fit and least squares regression line, LSRL, interchangeably, there is an important distinction between them. A line of best fit is a general term for any line that appears to fit the data well and can be drawn by eye or estimation, meaning different people might draw slightly different lines. On the other hand, the least squares regression line is a specific type of line of best fit calculated using a precise mathematical method that minimizes the sum of squared results. This means for any given data set there is only one unique LSRL, while there could be many different lines of best fit drawn by eye. Okay, so now I'm going to take you back over to GeoGebra and show you step by step how to do this. This is how to find a least squares regression line on GeoGebra.com. We're going to click Start Calculator. Okay. Over here, we're going to select Table. Okay. So we're going to enter our X values down here, and I'm just going to make some random ones up. We're going to say 1, 2, 3, 4, 5. Okay. And look, they're not showing up. Oh my goodness. But it's okay. That's because we don't have Y values yet. So we're going to come up here and we're going to enter some Y values. I'm going to enter random junk. I'm just going to like pound keys. Sure. That sounds great. Okay. It auto-populated this Y1 here, so you don't need to worry about that. Now, I can't see anything on here, right? So what I'm going to do is come over here to this little gear, which is the settings icon. We're going to click it, and then we're going to click... Oh, they lied. This is the tutorial the book gave me, and it's supposed to say zoom to fit. And I don't see any of these being zoom to fit. Wow. They lied. They lied. Let's go open settings. Is there zoom to fit? They lied, they lied, they lied. What if I just, nope. Wow, okay, so I'm just going to zoom out until I can see where these are. Okay, so here's my random points. Okay, my points don't make a straight line, but that's because I was just throwing random crap in there. Okay, we're going to come over here to the Y1 and click on the three dots to get a drop-down menu, and we're going to go regression. Okay, we need to make sure this is set on linear. And then it comes down here and it says our formula is y equals ax plus b. We're used to this being an m, but it doesn't matter what this variable letter is, so don't stress. Okay, let's look at the parameters. It says a is equal to 12.3 on my line, and b is equal to 7.3. 12.3 is going to be our slope because that's where it plugs into our formula, and 7.3 is going to be our y-intercept. Okay? That's all you need to worry about on here. We're going to go ahead and click plot. And look, it has a line of whatever it is, squares, least squares progression line. That's what it is. Okay. So I can make this graph bigger to show more by clicking right here and dragging away my table. Okay. So that it shows us more of this. Now we're going to click on my line right there. Okay. And it brings up this little menu right here. If I click on these two A's, okay, I can click on, it says show value. Pink. And look, here's my formula right here. I can move it so we can see it better. This gives us our formula written in the y equals mx plus b standard form that we want to see. Okay, so this did all of the work for me. That's all I had to do was enter the information into the table, follow those steps, and it gave me my formula. Now, when you're all the way done with this and you're ready to move on to your next problem, how you get rid of all of this, they called this a hamburger icon. I've never heard of that before. But you come up to these three lines, you click it, and you're going to go clear all, and then you want to discard it because there's no reason to save this. And we're back to completely clear. That's how you use GeoGebra to do this. Okay, now that we know how to have GeoGebra do all the work for us, these are the steps that you need to put in your notes, okay? You can always come back to this video and look at my little tutorial again, but this needs to go in your notes. Pause it, write it down. You need to be able to do this over and over for this lesson, and I'm sure for the unit test, okay? And by the way, this reminds me of Five Nights at Freddy's. Okay, here's example number 1. Let's work through this together. Determine the least squares regression line from the following table. Okay, so in order to do this, we're going to have to pull up GeoGebra. Okay, we're going to use our steps to find out the least squares regression line from this information. So first we're going to come over here to table. Okay, we're going to put in our x values and our y values. So I'm just going to, okay, never mind. We're going to go 0, 1, 2, 3, 4, 5. Okay, come back over here over to the y column, and we've got 1.5, 1, 3, 3, 5, 5.5. Okay, there's our table. Next, gotta look at my notes. We're gonna go, the zoom to fit didn't work, so we'll just zoom out so we can see the points. Okay, then we're gonna come to this drop down menu, and we're gonna go regression, make sure it's set on linear. It gives us our information right here. We'll go ahead and plot it. Okay, and then we can go and get rid of our table now because we just want to see our graph. Click on here, click on the A's, click on show value, and it gives us our formula. Okay, so you can see this goes to a million different places. I'm sure they won't do that because that is how they roll in this. So they said it's 0.91. Okay, so they cut it right there at the hundredths. X plus 0.88. Okay, all of that made sense. Let's go to example number 2. First thing we need to do is clear all so we can start over. Okay, consider the function y equals 2x minus 3. Determine the least squares regression line for this function. Okay, so what we need to do here is we need to create a table first. It has not provided us with a table. So the way that you would do this, let me pull up my tools. Tools, where are you? Right there. Quit being so tooly tool. Okay, so the way you would do this is you would go like X, Y, make a table. Okay, and we're going to put in values for x. So we're going to do like 1, 2, 3. That's as far as I'm going to go because that's the space I have. We're going to take our formula and we're going to have y equals 2 times x, which our first x is 1. Is that a minus? I have old lady eyes. Minus 3, which is going to give us y equals 2, because 2 times 1 is 2, minus 3. So y is going to be equal to negative 1 here. Okay, we're going to continue to do that. Let me grab my eraser and erase all of this. So now we have, give me my marker, 2 times 2 minus 3, which is going to give us 4 minus 3, which will give us a positive 1. Let's erase again. Chink, chink, chink. And let's go 2 times 3 minus 3 will give us 6 minus 3, which is going to give us 3. Okay, so here's some data. Let's come back over here to our x values. We have 1, 2, and 3. We have negative 1, 1, and 6. Let's see if this is enough information for it to do a regression. They've been using like 5 points or more, but this is how many I have. So let's come here and go regression. Okay, it gives us this information. Let's go plot, and then we'll click on the line, the A's, show value, and it gives us this formula right here. Okay, so they did 0, 1, 2, 3, 4. Okay, and it says, oh, and they wanted us to use a spreadsheet calculator for this, but it didn't specify what a spreadsheet calculator is or where to find one, and I don't even know what that is. So we're ignoring that. We're just using GeoGebra, because guess what? In the end, it doesn't matter. It's supposed to do the same thing. So anyway, in the end, the equation y equals 2x minus 3 ends up being the line of regression, which is obvious because that's the equation we used to make the table in the first place. Okay, so you could just do a line. You could come back and do like algebra and enter y equals 2x minus 3, and it's going to give you an exactly straight line. These points don't line up exactly on the line because I used the table we created. But this one, if you look at this graph, you can see they're all exactly on the line. Okay, notice that the least squares regression line intersects each point directly here. Okay, no residual exists between any of the points in the lines for their graph. Mine has a little bit of a residual, okay, and that may be because I only did 3 points. If I'd done more, they probably would have all landed on the line like this. Okay, point of this question is they wanted you to use like the spreadsheet calculator, and I don't know how to do that, and it doesn't matter at the end of the lesson. So anyway, all right, let's move on to question 1. This is your turn. It says use the table and GeoGebra to determine the least squares regression line. Round your answer to the nearest hundredth, and it wants to know the value for y. Oh, it's the formula. Y equals something x plus something. Okay, so go ahead and pause the video, figure it out, come back. So I'm going to go through our steps over here and put in our values. We have 5, 10, 12.5, 13, 15, and 17. I'm going to scooch this over a little bit so I have more room. I'm going to come up here and go 15, 16, 11, 10, 13, 12. Okay, and then we're going to go 3 dots, regression, plot. We're going to zoom out so we can see it. There it is. Okay, we're going to click on the line. Click on the line. There we go. A's, show value, and there's our formula. So it wants us to round to the nearest hundredth. So that means that our formula is going to be y equals, I'm going to write it down here because I'm not going to fit it in there. Y equals negative 0.33. That 7 makes us round it up. X plus 16.79. There is our formula. Okay. Let's move on to question number 2. Use the table and GeoGebra to determine the least squares regression line. Round your answer to the nearest hundredth. Pause the video and go do it. Okay, so first thing we're going to do is go table, fill in our x values. We have 1, 2, 3, 4, 5, 10. It's a little random. And then in the y values, we have 6, 5, 7, 7, 6, 7. Okay? 3 dots, regression, plot, zoom out so we can see it, click on the line, 2 A's, show value, and here is our formula. They want us to round it to the nearest hundredth. So our formula is going to be y equals 0.13. We don't need to round because the next number is under 5. X plus 5.7. The number after 8 is 5 or above, so we need to go up. So it's 5.79. There is your answer. Okay, here is practice question number 1 at the end of the lesson. And so you'll want to write the answer down so you can enter it later. Okay. It says Devin creates a table showing 5 points. He uses a calculator to calculate the slope and y-intercept of the least squares regression line based on the points in the table. What is the slope of the line? Go ahead and pause your video, figure it out, come back. All right, so let's enter our data. We have 0, 1, 2, 3, 4. Scoot this over a little bit. We've got 12, 14, 16, 18, 20. 3 dots, regression, plot, zoom out so we can see it. Click on the line, 2 A's, show value, and here's our formula. Now remember, this is in the formula y equals mx plus b. M is the slope. So the slope of this line is 2. All right. Here's quick check question number 1. I will not solve this one for you, but I will tell you the steps you need to take to solve it. Use a calculator to determine the equation of the line of best fit for the data in this table. Round to the nearest hundredth if needed. So they want us to find our formula. So you're going to do all the normal steps we would. You'll click table. You'll input your information. Then you'll go to the 3 dots by the y and click regression. Then you'll click plot. And then you'll click on the line, and then you'll click the 2 A's, and it will show you your formula, and you'll be able to see which one of these is correct. Okay. Here is the next part of the lesson. Check in. What is the slope for the least squares regression line, and what is the y-intercept? The slope, I don't know how they got these numbers, because we have no table, we have no information. Ignore that. Here's example number 1. Given the data set which displays the relationship between rainy days and the days spent visiting the beach per month, interpret the slope and y-intercept from the linear model. What is the least squares regression line for the data? So how we solve this is we go ahead and do all the steps we did before. We enter all this information into GeoGebra and get our formula, okay? And it wants to know, wants us to interpret the slope. The slope for this one is 0.90. So that means it's going to go up almost a whole unit for every unit it goes over, okay? It's going to go up 9/10 of a unit and over 1 unit. Okay. So let's keep looking at this. Here is the regression line for the data. And interpret the slope and the y-intercept of the linear model. What do they tell us about the data? Okay. So the y-intercept is right here at 31. Okay. This is where it crosses the y-axis. This linear model represents a negative relationship. That means that as the number of rainy days increases, the number of days spent at the beach will decrease. So the rainier it is, oh, that's because this is a negative 0.90. It's hard to see that negative. Okay, it's a negative relationship because this is negative. Okay. The slope is negative 0.90, so for every additional rainy day, the number of days spent at the beach will decrease by approximately 9/10. Okay. The y-intercept is 31. This means that when a month has 0 rainy days, people will spend approximately 31 days at the beach. Okay. We'll keep working on this. It's okay if it's not all clicking. Don't stress too much. Here's a check-in. Match each possible interpretation of the slope or y-intercept to the appropriate least squares regression line. So here we have our formulas, and here we have definitions. Our first one says a candle is 10 inches tall and burns down at a rate of 3 inches per hour. So 10 inches tall is going to be our y-intercept. That's our starting point. And then it's going to go down 3 inches every hour. So that's going to be a -3. That means this one has to go with that one right there. Let me... Okay. Let's see. A phone plan costs $35 per month with a $1 discount for every referral you make. So $35 is going to be our constant, which will be our b place, the last place in our y equals mx plus b. And the $1 discount will be a -1. So this one is coming down here to this one. A taxi charges a $5 boarding fee plus $2 per mile. So $5 is our constant. That will be the last number in it. And the $2 per mile is going to be positive. So that one goes with this top one. And then we have a plant grows 2 centimeters per day. That's it. So there will be no value for the y-intercept and just 2 centimeters per day. That's how that all goes together. Here's question 1. This one is yours. If you can't do it quite yet, it's okay. We're gonna get there. Okay, you should be able to answer this reasonably well. This linear model represents a positive or negative relationship. Let's stop and look at this. It's going up, up, down. Okay, so depth 10, 11, 20, 30, 30, 40, 40, 40. Okay, you know what? I'm just going to go ahead and graph this. This is going to be easier for me. Always for working smarter, not harder. So let's go ahead and just enter this information. We've got 10, 11, 20, 30, 30, 40, 50, 60, 73. Let's come up and over to our y values, and we're going to do 11, 105, 92, 84, 75, 73, 60, 50. Oh, nope, that's 50, not 90. Okay, let's do our regression and plot it. Okay, let's zoom out and look at it. There it is. Okay, we do have an outlier. I probably entered the wrong number, but you know, whatever, will do me. We'll do it. Okay, so here's our line. So this linear model represents a positive or negative relationship. Well, it's easy to tell from the line that we've got a -1 going, so it's not positive. This line is decreasing. Okay, the slope is 109 point. Oh, we need our formula. Let's get our formula. Where's our formula? Where's our formula? Where's our formula? Doop 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 doop. Our slope is -0.32, and it doesn't give us that option. Interesting. I must have entered some of this wrong. Because I am so talented. Let's come back here and look. 10, 11, 20. Yes. 30, 30, 40. Yes. 50, 60, 73. Yes. 11, 105. I bet this is just 15. I bet that's where it went wrong. I bet I typed it wrong over here, because that doesn't make any sense. I bet this one's wrong too. 84, 75, 73, 60, 50, 50. I bet this isn't 95. I bet this is like... Well, it could be. I don't know. I don't know. I probably did something wrong here. But anyway, when you have the correct information, this will be an obvious answer. I'm guessing it's going to be either -92 or... Yeah, it's going to be either -92 or -97. Anyway, this means that for every increase of 1 foot of ocean depth, the temperature will likely increase or decrease. Okay, well, it's obviously not going to increase or decrease by 100 and something degrees. That's ridiculous. I mean, like, no. So it's going to get colder the further you go down in the ocean, so it's going to decrease by about 0.92 degrees. So that's going to be your answer up here. It's going to be negative 0.092, and it's going to decrease by approximately 0.92. I don't know if that's the right one or not because it's covering up. Anyway, the y-intercept means that when the ocean depth is 0, the temperature, our y-intercept here should be 0 too, so I did screw this up. The temperature will be approximately, okay, so at the depth of 10, it's going to be 11. So it's going to get warmer and warmer as we go up, right? So at a depth of roughly, this is going to go up roughly 1 degree each time. So it's going to be real close to 0. So it's either going to be the 0.92 degrees or the 0 degrees for this answer. Okay. I'm sorry that I got this information wrong. When you go in to do this lesson, I'm sure you'll be able to figure out what went wrong, because it's GeoGebra's job to fix all of this. I apologize that I don't care enough to go and fix this. Here's question 2. Interpret the slope and the y-intercept of the following linear model, which represents the cost of potatoes by pound. Okay, pause it, figure it out, come back. Let's see if I can succeed at this one. Okay, we've got 1, 2, 2, 3, 4, 4, 7, 8, 8. Okay. Let's come up over here, come over. We've got 0.79, 3, 1.39, 2.201, 4.15, 6.296, 7.19. Okay. Let's get a regression going. Chink, plot, chink, a value. Okay. So what this tells us is the linear model represents a positive relationship, which we can see. It's sloping up because the slope is 0.82, which we agree with. This means that for every increase in pound of potatoes, the price will increase by 82 cents. The y-intercept is approximately 0, which means that when you are purchasing 0 pounds of potatoes, the cost will be $0, because why would you pay to get no potatoes? That makes no sense. There had to be bad information on that last table. I'm sorry. Here's practice question number 2. This is at the end of the lesson. Which option could be the slope for this data set and the correct interpretation in this context? The video, see if you can figure it out and come back. So if we look at these answers, our slope is either going to be 10 or 1/10. So if the slope is 10, we got to look down here. We're going by 1s here. We're going by 10s here. If the slope is 10, it means we're going up 10 over 1, 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 okay? If the slope is 1/10, it means we're going over 1, up 1 over 10. Okay, so obviously these two are out. That doesn't make any sense looking at that graph. So these 1/10 options are gone, okay? So the slope is 10, meaning for each hour of study, the score goes up 10 points. So we go up 10 over 1, up 10 over 1 hour, up 10 over 1 hour, up 10 over 1 hour. That makes sense. The slope is 10, meaning for each point on the test, you must study for 10 hours. So to get 1 point, you study for 10 hours? No, that doesn't make any sense. Okay. Here's practice question number 3. Claire got a part-time job pet sitting. She received a $150 sign-on bonus and then gets paid each month depending on how many hours she works. The graph shows the line of best fit displaying the number of months she has worked compared to the total amount of money she has earned. Which of the following options is a correct interpretation of the y-intercept at 0, 150? So we're looking at this point right here. Okay. Option 1 says Claire earns $150 for every job she completes. Option 2 says Claire earns an average of $150 a month. And option 3 says the initial amount of money Claire earns is $150. Pause it, figure it out, come back. Well, if you read this carefully, you know that this is the right answer. But I'm gonna prove to you that these ones are wrong. If she does gets $150 for every job she completes, then at one job she should be at $150. She's not. She's at 200. At a second job she should be at 300. She's not. So this obviously doesn't work. And then to say Claire earns an average of $150 a month, that means that she'd be at 150 here. She's not. She'd be at 300 here. She's not. Okay, so that's totally right. Here's quick check question number 2. I won't answer this for you, but I'll tell you how to figure it out. This table displays the number of hitting attempts, x, and their corresponding kills, f of x, showing the relationship between attempts and successful hits. Ava is a middle hitter of her club volleyball team. The table displays the number of hitting attempts she had in the last 6 games compared to the number of kills, which is when a hitting attempt hits the ground and scores a point. If the slope for the line of the best fit is 1/2, interpret the following representations of the slope and identify which statement is accurate. Okay, so it tells us right here that our slope is 1/2, and it wants us to interpret that slope. Okay, what that means is they're saying Ava has about 2 kills for every game. Ava has about 1 kill for every 2 hitting attempts. Ava has about 2 kills for every hitting attempt, and Ava's number of kills increases by 2 for every game. I'll give you a hint. This is x, so obviously this is this axis, and it says x is hitting attempts. So hitting attempts, and so f of x is also y, so this is going to be kills. Okay, this is the way it's going to be set up, and we know that our slope is 1/2. So you're going to go up 1/2, up 1/2. Your line's going to look something like this. Okay, so Ava has about 2 kills for every game. That means we don't have games at all. That's saying something. Ava has about 1 kill for every 2 hitting attempt. So here's 1 kill, 2 hitting attempts, 1 kill, 2 hitting attempts. Okay. Ava has about 2 kills for every hitting attempt. 1 hitting attempt, 2 kills, 1 hitting attempt, 2 kills. Ava's number of kills increases by 2 for every game. Again, we don't have game on here at all. Here's quick check question number 3. An elephant calf is born weighing 282 pounds and gains about 2.5 pounds each day for its first year of life. After 1 year, the calf weighs approximately 1,195 pounds. The graph represents the line of best fit for the data. Which of the following interpretations of the slope is accurate? So we're just looking at the slope, trying to figure it out. Okay, it says the calf gains 737 pounds over 182 days. So 182 days is about here, and it says it's going to be 737 pounds. The calf gains an average of 1,195 pounds, which is right about here, over 1 year of life. So that would be right about there. The calf gains 5 pounds every 2 days. And that, it would say, here's day, so here's day 1. Okay, that it would be right there, and it's going to gain 5 pounds from the day before, another 5 pounds, another 5 pounds, another 5 pounds. Okay, the calf gains 365 pounds in 913 days. So we started here, and then in 913 days, which is somewhere clear over here, it says it's going to gain 300 pounds. Okay, figure out which one of those makes the most sense. Last part of the lesson, and I'm not sure how to say this word, so I'm guessing, is interpolation and extrapolation. I know it's extrapolation, so I'm guessing this is interpolation. Interpolation is to estimate values of data between 2 known values, and extrapolation is to predict by projecting beyond the known values of the explanatory or independent variable. Here's example number 1. The cost of a flight is related to the distance traveled. Thus, the farther you fly, the more you pay for the flight. Use the data to answer the questions. Keep in mind that x is the distance in miles and y is the cost in dollars. The line of best fit is, and here's your formula. According to the data, what would a flight that travels 525 miles cost? Round to the nearest dollar. So in order to solve this, first we're going to see if it's an interpolation or an extrapolation. This is an interpolation because 525 miles is within the known values. It's higher than this value and lower than that one, so it's interpolation. It's inside our table of values. Okay. Substitute x equals 525, because that's what it's asking us, into the line of best fit equation and simplify. So we have y is equal to 0.0824 times x, which in this case is 525, plus 34.8. totally getting my calculator for this. Okay, so we have 0.0824 times 525, which gives us 43.26, plus 34.8 gives us 78.06. So $78.06, but it wants us to go to the nearest dollar, so it's going to be $78. Okay, right there. Here's example number 1 again. This is another question in the same one. So we have all the same data, and it says, according to the data, how much would a 3,025-mile flight cost? So we have y. Y equals 0.0824 times our x this time is 3,025 plus 34.8, which is our y-intercept. Let's bust out our calculator. We're going to go 0.0824 times 3025. Ooh, I did that completely wrong. 3025 gives us 249.26 plus 34.8. And they want us to round to the nearest dollar. It's $284.06, so it's just going to be $284. Okay. And now, and this one is extrapolation because the highest our table goes is 2,250 miles, and this one is 3,000. So extrapolation is outside of the table, exiting the table. Okay. And it would cost $284, which is what we said. Here's the next question, same information. Does the line of best fit over or underestimate a flight that is 800 miles? Okay, so they say for 800 miles, the exact cost is $95, okay? And if you look right here, the line of best fit is above that, so they overestimate how much it's going to cost, okay? So you can get the exact amount by doing the math, by doing y equals 0.0824 times 80. Is that right? Oh, 800. 800 plus 34.8. Okay, and let's grab a calculator. And we have 0.0824 times 800 gives us 65.92 plus 34.8 gives us 100.72, okay, which is right here, okay? So this line says it's going to be $100 to fly, but they really only charge 95, so they overestimated the cost. Another check-in, if someone underestimates a value, what are they doing? They are estimating a value that is less than the known value. Here's question number 1. This is your turn. Some homeowners were surveyed that had plumbing work done in the last few months, and the data is shown in the table. X is the number of hours worked, and Y is the total cost of the repair. The line of best fit is Y equals 25X plus 50. According to the line of best fit, what is the estimated cost to have a plumber do a repair that takes 1.5 hours? Pause it, figure it out, come back. So we're going to take our formula. I guess I should get a color that will actually show up. Y equals 25 times X. Our X for this one is 1.5 hours, so 1.5 plus 50, and we're going to solve that. Calculator time. 25 times 1.5 gives us 37.5, plus 50 gives us 87.5. So it's going to cost us $87.50, okay, to get work done that takes 1.5 hours. Where am I? Where am I? Okay, question number 2. This is all the same information. X is the number of hours worked and Y is the total cost of the repair. According to the line of best fit, if a plumber charges $125 for a repair, how long might the plumber work? Pause it, figure it out, come back. So the amount that he charges for the repair is Y. So for our formula, we're going to put 125 for Y equals 25X plus 50, and we're going to solve for x. So let's subtract 50 from each side. That's going to leave us with 75 is equal to 25x. We're going to divide both sides by 25, which is going to leave us with x is equal to 3. I believe I'm going to double check. Double check. 75 divided by 25. Oops, I guess it would help if I actually put 75 and not 72. 75 divided by 25. It is 3. Oh my gosh, I did it right. So it'll take 3 hours if he got paid that much. Okay. Here's question 3. Same information. A plumber estimates it will take 5 hours to complete a repair and quotes a homeowner $200. Should the homeowner hire the plumber? Pause it, figure it out, come back. So it says it's going to be $200, so that's our y. If we have 200 is equal to 25 times 5 hours, that's our x, plus 50. We're going to see if they're getting a good deal or if they're getting ripped off. Okay, so the 200 we're going to leave alone, equals 25 times 5 is 125, plus 50, which then gives us 200 is equal to 175. So he says he's going to charge him $200 when if they paid like the hourly rate, they'd only have to pay 175. So should they hire him? No, scammer. So more about interpolation and extrapolation. Interpolation is when you predict a value that falls within the range of your original data, and extrapolation is when you make a prediction outside of the range of your original data. Here's example number 2. A coffee shop tracks its ice cream sales. They find that sales can be modeled by the linear equation S equals 10t minus 50, where S is the number of ice cream cones sold and T is the temperature in degrees Fahrenheit. The data was collected on days when the temperature was between 60 and 90 degrees. So first, predict the number of ice cream cones sold at 75 degrees and explain if the prediction is valid. And second, predict the number of ice cream cones sold at 30 degrees and explain if the prediction is valid. So first let's do 75 degrees. We have S equals 10 times 75, which is our temperature, minus 50. Let's grab my calculator because I don't want to try. So 75 times 10 gives us 750, minus 50 gives us 700. So when it's 75 degrees out, they're going to sell 700. Is that prediction valid? Yeah, probably. Okay. Let's do it over here for when the temperature is 30. S is equal to 10 times 30 minus 50, which is going to give us 10 times 30, 300 minus 50, which is going to give us 250. Now, do you think they're going to sell 250 ice cream cones when it's 2 degrees below freezing outside? Probably not. They might not sell any ice cream. And that's what all of this garbage says. The important thing here was this prediction might be mathematically correct, but not valid in the real world. Check in. A local animal shelter tracks the weight of a puppy for its first 8 weeks. The puppy's growth is modeled by the linear equation W equals 1.5t plus 4, where W is the weight in pounds and T is the time in weeks. Use the model to predict the puppy's weight at 2 years, 104 weeks. So we have W. Oh, I need a different color. I need a different color. Thank you. W is equal to 1.5 times 104, because that's how many weeks we're looking at, plus 4. Let's grab our calculator. We've got 104 times 1.5 gives us 156, plus 4 gives us 160. So that means that at 2 years the dog would be 160 pounds. Is this a valid weight for a typical adult dog? For a typical adult dog, no. For a dog I would buy, yeah, my dogs are all huge and disgustingly massive and break. Straight up just skipped a whole question because it made absolutely no sense to me. And I don't think there's anything like it on the end. It had like this strange percentage crap going on that didn't make any sense. Anyway, based on U.S. households tend to consume more electricity based on research when the weather is warmer. Use the data to answer the questions. Keep in mind that X is the daily temperature in degrees Fahrenheit and Y is the average amount of electricity consumed in kilowatt hours. The best line of best fit is Y equals 0.445X plus 7.47. How much electricity will be consumed by a household if the average daily temperature is 77 degrees? Round your answer to the nearest kilowatt hour. Pause it, figure it out, come back. Okay, so our formula is Y is equal to X is the daily temperature, so we've got 0.445 times X, which is the temperature. In this case, it's 77, plus 7.47. Let's bust out my calculator. We've got 0.445 times 77 is 34.265 plus 7.47. And they want it to the nearest whole kilowatt hour. So our answer is 41.735. So it's going to be 42 as our answer. Ta-ta-da, I did it right. Here's question number 2. So this is all the same information. It says how much electricity will be consumed if the daily average temperature was 98 degrees. Round your answer to the nearest kilowatt hour. Pause it, figure it out, come back. So this time we have Y equals 0.445 times 98. Is that right? Yes. Oh my gosh, that 9 is special. Plus 7.47. Let's grab the calculator. And we're going to clear all of this and go 0.445 times 98 gives us 43.61 plus 7.47 gives us 51.08. They want the nearest kilowatt hour, so our answer is 51. All of the same data, and it says, does the line of best fit over or underestimate the average electricity used by a household when the temperature is 68 degrees? So at 68, we're looking at this dot right here, okay? And you can see that the line underestimates it, but we'll do the math just to be on the safe side, okay? So Y equals 0.445 times X, which is 68, plus 7.47. Calculator time. 0.445 times 68 gives us 30.26 plus 7.47 gives us 37.73. So rounded to the nearest whole one, it would be 38. But if we look over here on the chart where we actually have 68, it's 38.7. So it underestimated it. It was actually warmer. So it says underestimates right here. End of the lesson. Practice question 4. The loan amount is a function of time and can be represented by the line of best fit. Y equals 15,413 minus 1,635x, where x is the number of years. How much is left on the loan after 9 years? Pause it, figure it out, come back. So now this one's written a little bit different. This is written as y equals b minus mx. So keep that in mind. It doesn't matter, it'll be fine, but we have 15,413 minus 1,635 times x, and x in this case is 9. So we need to do PEMDAS, so we do this part first, okay? We're going to go 1,635 times 9 is going to give us negative 14. Come back, calculator. 715. So now we have 15,413 minus 14,715 gives us 698. So you've almost got the loan paid off after 9 years. Practice question number 5. Use the linear model to make a prediction. The line of best fit, y equals 0.37x plus 5, represents the tolls you pay after driving a specific number of miles. How much would it cost in exact change to travel 70 miles? Okay, so y equals 0.37 times 70 plus 5 calculator. Oh, I'm sorry. You're supposed to be figuring this out on your own. I hope you're doing that. 0.37 times 70 gives us 25.9 plus 5 gives us $30.90. Okay. Here's the quick check. Use the linear model to make a prediction. The line of best fit is blah, represents the tolls you pay after driving a specific number of miles. What prediction can be made based on this line of best fit? Is this the same one? It is the same one, okay? So it says if you drove 10 miles, you would pay $42. So you would plug 10 in for X and solve it and see if Y is 42. If you can spend $42 if you drive 100 miles, so plug in 100 for X and see if Y is 42. You can drive 50 miles and spend less than $20, so plug in 50 and see if Y is less than $20. You can spend less than $30 to go 75 miles, plug in 75 for X, see if Y is less than 30. Quick check question 5. This table shows the relationship between miles run, X, and weight in pounds, Y, indicating how weight changes with running distance. The weight of a cheetah can be based on the number of miles they run a day. The line of best fit for this data set is blah. The table represents the scatter plot of data. Find the weight of a cheetah that runs 7 miles and state whether the extrapolation or interpolation is occurring. So for 7 miles, you would take this formula, you would plug in 7 for X and solve it. Y is going to be the pounds, so you'd find that. And then you have to decide if it's interpolation or extrapolation. If we're dealing with 7 miles, this is the number of miles right here, okay, and this is the weight. Is 7 within the bounds of our table? If it is, then it's interpolation. If it's not, it's extrapolation. And you know, I got to see koalas in real life, and they were a lot smaller than I thought they were going to be. They're the perfect size for cuddling. I'm sure they don't want to cuddle, but they would be great for cuddling.